All right, in today's lesson here, we're going to look at coming up with a formula to calculate the distance from a point to a line. So let's take a look at a setup here. Let's say we have a line, and we'll define this line to be ax plus by plus c equals 0. And we have a point here. This is going to be given to you, so I'll let this be p naught. We'll denote this x naught, y naught. Now, the shortest distance from a point to a line is going to be a line that meets our line here, ax plus by plus c equals 0 at 90 degrees. So now let's take a look at another point on our actual line here. I'll let this be P1, call this x and y. So again, our goal here is I want to create a formula that's going to calculate the distance of this line segment. This would be the shortest distance from a point to a line. Obviously, there's an infinite number of distances from a point to a line, as you can see here. You can choose any one of these, but the shortest distance is going to be the one that meets at 90 degrees, and that's what we want to calculate. I'm going to let this be d. Now, right away, if I let theta be the angle here, we know that the length of the shortest distance, or d value here, by definition would be the magnitude of P1 P naught times the cos of theta. Now I'm going to let this point right here be r. So this length right here that we're interested in finding a formula for can be expressed as the magnitude of P1 P naught cos theta, which is equivalently equal to the magnitude of P naught r. Now let's take a closer look at this formula and see if we can manipulate this in any way to get a nicer formula for ourselves here. So first of all, take a look. All right, so I'm going to take a look at P1 P naught. And by definition, the vector P1 P naught is going to be x naught minus x, y naught minus y. If I take P1 P naught and take its dot product with the normal, again, I'm going to let my normal vector here just be the vector AB. When you do that, you end up getting here ax naught minus ax plus by naught minus by, ends up being the dot product here. So now let's try to put a bit of this together here. I now know that the magnitude of P1 P naught cos theta, I know that's equal to our shortest distance. This is what we want to find. This is my d value, P naught r. Well, I also know that P1 P naught dot your normal is the magnitude of P1 P naught times the magnitude of my normal cos of the angle between them. Therefore, we have the magnitude of P1 P naught to the cos of theta is equal to P1 P naught dot my normal over the magnitude of my normal. Again, the only thing I did was I grouped these two together and divided out my normal here. I have this representation. So continuing this on here, I now know that my d value, which is what I want to find, is equal to the magnitude of P naught r, which we just discussed is equal to the following here. And that is exactly equal to P1 P naught dot my normal over magnitude of my normal. But as I just discussed above, P1 P naught dot my normal is equal to the following here. So this is exactly equal to ax naught minus ax plus by naught minus by all over the magnitude of my normal. But your x and y value here, if you recall, your x and y value is a point on the actual line. So therefore, it must be the case that ax plus by must equal negative c, right? Because this is a valid point. The P1 value is on the line, so therefore the equality holds. So therefore, ax plus by must equal negative c. So therefore, we can now get rid of negative ax and negative by and change that to a positive c value here. So we get ax naught plus by naught plus c over the magnitude of n. And again, just to ensure we do have absolute value, do have a positive length, or take the absolute value of this expression. So therefore, we have a formula here. The shortest distance from a point to a line is given by the following: the magnitude of ax naught plus by naught plus c, where x naught and y naught is a point given to you. That's the point you want to find the distance to the line of. And the a, b, and c are the values from your line itself. And the magnitude of n is the magnitude of your normal vector to your line. All right, now that we have a formula for the shortest distance from a point to a line, let's take a look at some application. All right, so we want to find the distance from a point to our line here. And we just derived the formula here. I know that the distance from a point to a line is going to be the absolute value of ax naught plus by naught plus c over the length of a squared plus b squared. So in this case here, my a value is 5. My x naught value is the x coordinate given to me, so -6. My b value is -3. The y coordinate of my given point is 4. And my c value is 15. All over the square root of 5 squared plus -3 squared. Continuing here, we get -30 minus 12 plus 15, all over the root of 34. And taking a look here, this is going to end up being -27 because we are taking the absolute value, right? Distance is a positive term. This ends up being equal to 27 over the root of 34. So in this example here, the shortest distance from the point to this line is equal to exactly 27 over the root of 34. Let's take a look at another example. All right, so now we're going to take a look, and this formula we've derived and we just used in that previous example can be extended to R3. So you have a similar formula in R3. This will be the distance from a point to a plane is given by the following. So ax naught plus by naught plus c, z naught plus d over the magnitude of a squared plus b squared plus c squared. So in this example here, your given point p naught would be the x naught, y naught, and z naught. And then the plane itself would be your ax plus by plus cz plus d equals 0 would be your plane. So this is like where you're pulling the variables from. Same idea. You're calculating the distance from this given point to a specific plane that they're asking you to look at here. Let's take a look at an example. Find the distance from a point to a plane. So I've got my point and I've got my plane. So this is just an extension of what we just did in the previous example. So the distance here is absolute value of a, which is 8, times my given x coordinate. Then I've got my b value times my given y coordinate, my c value times my given z coordinate plus my d value, all over the square root of 8 squared plus -4 squared plus 8 squared. So if I go to calculate this here, the distance here is going to equal -8 minus 8 minus 32 plus 3 all over. This is going to be 64 plus 16 plus 64. And if I calculate this here, you're going to get, because you take the absolute value of this, you're going to get 45. And that's going to be 45 over 12, right? Because this will end up being 144. The square root of 144 is 12. And that'll reduce to become 15 over 4. So in this example here, the shortest distance from the point to the plane is 15 over 4. So in the next example here, they want us to determine the distance between two planes. So notice right away, this question would not make sense unless these planes were parallel, because then the distance between two parallel planes would always be different depending on what points you're referencing. So I'm going to go ahead and check my normals here. If I check the normals for both plane 1 and 2, you'll find quickly that the normals are collinear. They're in fact equal. They have the exact same normal value. The only difference here is their d value is different. So visually you kind of have something, might look something like this, and you've got a second plane, two parallel planes looking like this. Perhaps this is plane 1 and this is plane 2. Now, in this example, they want the distance between these two planes. Because the distance is uniform between them, the planes are parallel, so their distance is consistent. Whether I take any 2 points I choose, those distances between those planes will all be the same. So the strategy here, what you do is find a point on, let's say, plane 1. Again, I could have easily found a point on plane 2, but find a point on plane 1. So what is a point that satisfies plane 1? Well, a point that satisfies plane 1 would be the point -2, 0, 0. And I know that to be the case because if I sub this point into this equation, it satisfies it. So therefore, I found a point on the plane. What I'm going to do is I'm going to calculate the distance from this point to plane 2. And this will be my d value. So this is exactly equal to the absolute value of my a value times my given x coordinate, my b value times my given y coordinate, my c value times my given z coordinate, plus the d value, which is 16, all over the square root of 2 squared plus -1 squared plus 2 squared. So if I do my math on this, I end up getting here absolute value of 12 over the root of 9, and you end up getting 12 over 3, and the distance between these two planes is uniform, it's 4. Also, the distance between any point on the plane to the other plane is also 4. So this is an example of you have two parallel planes and the distance between them is the same. The strategy is to pick a point either on plane 1 and then calculate the distance to plane 2, or pick a point on plane 2 and calculate the distance to plane 1, adjusting your d value based on what formula you're going to be using. All right, so this is an application question of distance between two planes. Let's take a look at another example. All right, for the following question here, you're given two skew lines. These lines are skew. You can check them yourself, but quickly you can see these two lines are not collinear, so they either intersect at a point or they're skew, and you can go ahead and do it yourself. But these two lines are skew, and we want to find the distance between them. The strategy is what I'm going to do is I'm going to create a plane, call it plane 1, and plane 1 is going to consist of my vector, let's call this R1, plus it's going to have on there the direction vector 1, 1, 2. So what I'm going to do here is I'm going to grab a line, a vector on my plane, and then the direction vector from the other line and put it on that plane. I'm going to create a plane called plane 1. Then I'm going to do the exact same thing with plane 2. I'm going to create a plane, and that plane is going to consist of vector R2 this time, vector equation of a line R2, plus I'm going to grab my direction vector, this time 1, -1, 1. And I'm going to create a plane based on those two direction vectors and a point. By doing so, what I've done here is I've created a situation where these two planes are parallel. You'll notice that since both these planes contain the same two direction vectors, their respective normals should be collinear to one another, and you therefore have created two parallel planes. So I want to go ahead now and I want to create those planes first. Once you've created the two parallel planes, you're kind of back to the previous example. So I'm going to find my normal for plane 1. So the normal for plane 1, I'm going to go ahead and take my cross product. I'm going to take 1, -1, 1, and cross that with 1, 1, 2. So when I go ahead and take my cross product here, I end up getting here -2 minus 1 is -3. And I end up getting here 1 minus 2 is -1. End up getting here 1 plus 1 is 2. So I'm getting the normal for my vector here is going to be -3, -1, and 2. So if I go ahead and take my normal dot my first direction vector here, I'm going to get -3 plus 1 plus 2, which is 0. And my normal dot my second direction vector here is -3 minus 1 plus 4, also equal to 0. So this is perpendicular to this plane and therefore this plane as well. So solving for my d value here, I just need to sub in a point on the equation. So for plane 1, I've got -3x minus y plus 2z plus my d value equals 0. Grab a point on my plane, so let's do -2, 1, and 0. So that'll be -2, 1, and 0, and I can solve for my d value here. D ends up coming out to be 7. So now I'm in a situation where I have a plane 1, and the equation of plane 1 is -3x minus y plus 2z plus 7 equals 0. And I want to find the distance. The initial question was the distance between two lines that are skew. So I wanted to find the distance between these two skew lines. What I did was I created two parallel planes, and now the distance between any two parallel planes is the same. So any distance I find here, you're going to get all the same lengths. The distance between any two parallel planes is the same. In particular, the distance between the skew line here and this skew line here will also be the same. So I've kind of simplified the question to just find the distance between two parallel planes. So now I have an equation of a plane. I can just grab a point on this plane here. So a point on this plane that I'm going to use on plane 2 would be the point 0, 1, 0. I'm going to go ahead and use that point. So my point here is going to be 0, 1, 0, and I'm going to use my formula. So my formula tells me the shortest distance between these skew lines is going to be the absolute value of A times my x coordinate, then my b value, times my y coordinate, then my c value, times my z coordinate plus 7, all over the square root of negative 3 squared plus negative 1 squared plus 2 squared. So calculating this here, I get my d value is equal to negative 1 plus 7 all over the square root of 9 plus 1 plus 4. Ends up being here 6 over the root of 14, which is approximately 1.6 units. So therefore, in this example here, the distance between these two skew lines, so the distance between these two skew lines is equal to 1.6. All right, that concludes today's lesson on distance from a point to a plane and distance between skew lines.